Hey everyone and welcome. Today we're going to take something you see all the time, a simple circle, and unlock a pretty amazing secret that's hiding inside. We're going to find out what happens when we let a point on that circle just spin forever. Trust me, you're going to be surprised by what it reveals.
So this is the big question for today. If you have a point that just keeps going around and around a circle, what is it actually doing? I mean, it seems obvious, right? It's just going in circles. But what if I told you that by going in circles, you're actually creating something way more powerful?
So here's our first move. We're going to take this circle that we know and love, and we're going to, well, unwrap it. We're going to completely change how we look at it. We're shifting from seeing just a static point on a circle to seeing the beautiful, dynamic path it carves out as it moves. Now, before we get ahead of ourselves, let's just dial it back to something we already know. Remember the unit circle? And remember that sine of an angle, all that is the height. It's just the y-coordinate of your point. That's it. That's simple vertical line.
Okay, so what if we stopped thinking about just one single angle? What if we imagine that angle theta just spinning and spinning and spinning continuously? As it goes around and around, we're only going to pay attention to one thing, its height, its sine value.
And here it is. This is the big moment. When you plot that height against the angle as it keeps increasing, you're not making a circle anymore. You're making a wave. That repetitive circular motion, when you stretch it out over an axis, becomes this perfect, predictable, oscillating pattern. How cool is that? So this whole unwrapping process actually gives us two of the most important waves in all of math and science. You can think of them as siblings. They're born from the exact same circular motion, but they just have a slightly different starting rhythm. So let's meet the sine wave and its partner, the cosine wave. First up, we've got the sine graph. Its number one defining feature, its starting point. It always begins right at the origin, at 0. And from there, it's got this super simple rhythm. It goes up to its max, back down through 0, down to its min, and then back to 0. That whole dance happens over and over every 2 pi radii. And here is its sibling, the cosine graph. We like to call this one the bucket. And why is that? Well, instead of starting at 0 like sine, cosine starts at the very top, at its maximum value of 1. Then it drops all the way down to its minimum and comes right back up, kind of tracing out the shape of a bucket or a valley. So when you put them right next to each other, you can totally see they're related, right? The only real difference between them is where they start. Sine starts in the middle, at the origin. Cosine starts at the top, at its max. That's it. It is literally the exact same wave, just shifted over a little bit. The fancy term for this is that they're out of phase. And you can see their shared DNA right here. Even though they start in different places, their most important features are totally identical. They both take exactly 2 pi to complete one full cycle, that's their period, and they both go up to a height of 1 and down to a depth of -1, that's their amplitude. All right, that's enough theory. Let's get our hands dirty and see how we can actually use this stuff to solve problems. This is where the rubber meets the road, and where we'll learn how to sidestep some of the most common mistakes people make. Okay, everybody, listen up. If you remember literally one thing from this whole explainer, please make it this. This is the number one thing that trips people up. Just burn it into your brain. Sine starts at 0, cosine starts at 1. Got it? Awesome. It'll save you so much trouble down the line. All right, first little pop quiz. Let's say we have the function 5 times sine of x. Now that 5 stretches the wave vertically, right? So does that mean the graph now starts at 5? Or does it still start at 0? What do you think? So let's walk through it. The key is to always go back to the parent function. The parent here is just sine of x. And what do we know for sure? We know that sine of 0 is 0. So what's 5 times 0? Well, it's still 0. So even though the wave is 5 times taller, it doesn't change the starting point one bit. It still kicks off right from the origin. Okay, next up, let's zoom in on our basic cosine wave. If we're looking at just one full cycle, from 0 to 2 pi, can you tell me exactly where that graph hits its absolute lowest point? You don't even need to memorize a formula for this. Just picture that bucket shape in your head. It goes high, then 0, then low, then 0, then back to high. That lowest point is smack dab in the middle of the whole cycle. And what's halfway through a 2 pi cycle? It's just pi. So the coordinates for the minimum are pi -1. Simple! All right, for our last example, let's bring everything full circle, pun intended. If you were to draw both sine and cosine on the very same graph, where's the first place they would cross each other?
And the secret to this one is to go right back to where we started, the unit circle. Remember, the sine wave is just a graph of the height, the y-coordinate, and the cosine wave is just a graph of the width, the x-coordinate. So this question is really just asking, at what angle are the x and y coordinates the exact same? And we know that magical spot. It's at 45 degrees, or as we say in radians, pi/4.
So you might be thinking, okay, unwrapping circles is a neat math trick, but so what? Why does this actually matter? Well, it matters because these waves are not just drawings in a textbook. They are quite literally the rhythm of the universe. Take the electricity powering your computer right now. It is not a steady flow. It's a sine wave. The voltage flips from positive to negative and back again, and that oscillation is what lets power travel hundreds of miles from a power plant right to your room.
And get this, how fast does it flip? In North America, that electrical sine wave completes a full cycle 60 times, every single second. That's a frequency of 60 hertz. So every time you flip a light switch, you are plugging into the very same wave we just unwrapped from a simple circle. And that brings us to one last mind-bending idea to leave you with. We saw that sine and cosine are basically the same wave, just shifted. But here's a little sneak peek into calculus. The slope, the steepness, of the sine wave at any point is exactly equal to the height of the cosine wave at that same point. They're connected on a much deeper level than we thought. So if a relationship that profound is hiding in plain sight, what other secrets are just waiting to be unwrapped?